Awesome. Welcome back, everybody. Good afternoon. It's another lovely day outside. So today we are going to pick up where we left off with that slideshow. We're going to talk about troubleshooting welds, a whole bunch of different things to look at. Let's get to it today. Share screen here. Make it happen. So let's present this. Boom. Striking an arc, making a weld. Let's see. Yes, that's where we left off. Perfect. Striking an arc and making a weld. Two methods of doing this. The one I like is what I call the scratch start. So you basically take the end of the rod and scratch it on the plate like you're striking a match. You're going to do that quick. You're going to hold it above the plate. You're going to come down, you scratch the plate, hopefully initiate the arc, lift that rod off the plate, let the arc stabilize, then close up the arc gap and start your weld. That lifting off the plate is going to be important because you want that space for the arc to clear, and it needs to establish, get stable, then you can start your weld. Second method is going to be a tap start. Here we can see outlined, we got a scratch start and a tap start. So scratch, you take your rod from here, bring it down, scratch, lift it up. Hopefully it lights on you. And here, what we do is we tap our rod on the plate. I kind of give it a little mini scratch and then hopefully it starts up. If it doesn't, what we need to do is look at the end of the rod. If we cannot see the exposed metal core wire, then we need to break the end of the flux off. The flux is quite brittle though, so there's a method I use of doing that. I will reach down to the floor and I will scratch the end of the rod on the floor. The roughness of the floor will take that little slide cap off the end of the core wire and allow you to make electrical contact with the core wire and your workpiece. That way we'll get that arc, the electricity will flow, and we will get our arc initiation. I'll show you guys these when you get into class. It's pretty simple, but it's going to save you a lot of pain and misery. It's just an easy way to help you guys out. So work angle, we want that at 0 degrees, especially on what we're doing right now. If it's a joint like this, a butt weld, we want it at 0 degrees. If it's going to be something like a fillet weld, 45 works pretty well. Your weld position and what you're welding is going to dictate your rod angle. Incorrect rod angle can leave you with things like undercut and a bunch of other undesirable things. Potentially spatter, long arcing, lack of penetration on one side of the joint. List goes on. There's a ton of stuff, but I'm not going to worry about that too much right now. We're going to focus on the basics, and yeah, we're going to carry on here. It's travel angle. This one, important. You want travel angle. You can run 0 degrees. You can run straight up, down, vertical, but I like the 20 to 30 degree angle. A little bit of layback. What that does is it gets the electrode holder in your hand out of your face too. You can actually see your puddle a lot better when you lay that rod back a little bit, 20 to 30 degrees. Straight up and down is going to give you the most penetration directly in, but laying it back 20 or 30 is going to give you more buildup of your weld. So if you're looking for a little higher profile on your weld and to be able to concentrate that heat in there, that 20 to 30 degrees of layback is going to be, or lead angle. Here, they call it lead angle. I call it layback. It's gonna work well because often if you're working straight 90, that hand's gonna be in front of your face. You're not gonna see your puddle. Then you got to crane your head around at an awkward angle. So if you get that 20, 30 degrees of lead angle, your head's gonna be straight over your puddle. You will be able to see it nice and easy. And this can vary, but we don't want to go more than 30 because what that's gonna do is give us a longer arc than we want. That could lead to spatter, all sorts of things like that. So after striking the arc, maintain a 1/8 inch distance between the electrode and the workpiece. If the electrode becomes too short, electrode will get stuck to the workpiece or short out. Basically, you're not allowing the space for the arc to clear. It doesn't get to establish. And if the arc length becomes too long, you get spatter, you get undercut, you get porosity. What happens is that shielding gas goes away. Your arc's going to wander side to side. It's going to be kind of looking for a place to establish contact, but it won't be concentrated. So when we keep it nice and close to the plate, that crucible cup on the end of the rod here, we can see that right here, the cup is what we, well, got a thing we call a crucible cup, and it forms on the end of the rod as you weld. That's where the core wire burns away just slightly faster than the flux on the outside. This directs the arc towards the plate, keeps it more stable. If you got that way up off the plate, it's going to fan side to side, and it's not going to be very controllable. It's going to give you a poor result. All right, so travel speed. Travel speed is the speed at which the electrode moves along the base material while welding. So that's how quickly you move from one side of the plate to the other. Everybody thinks this is a quick process, and even on TV, they show it as a quick process. All the space and sci-fi movies got these fancy welding guns, and they weld things up real quick. Reality is, it's a fairly slow process. The amount of weld, the size of weld, the quality of the weld, all depends on the travel speed. So if you are moving too fast, you're going to end up with a quite thin, narrow weld with a lot of the V-shaped profile on it. It's not going to penetrate well. You may have undercut, you may have spattered slag. Generally, it's not going to be very visually appealing at all. We want our welds to look good. A good looking weld generally is a good weld. That's kind of one of the things about welding is if you get more comfortable putting it in, you get that bead uniformity, the size, the shapes, the ripples all the same. That tells me that you know how to control those variables. And when you know how to control those variables, generally you're putting in a good weld. So you can kind of make the correlation between a good looking weld and an operator knowing what they're doing. Too slow of a travel speed is going to result in a wide weld. So this weld here will basically get overheated on the top of the base metal. It'll puddle out, kind of like you're melting a chunk of ice, and it, how it just creates a big puddle. That's kind of what's going to happen. When we overheat that base metal, the weld's going to become too wide. It's going to be hard to control. Anything outside of a flat position is going to be very difficult to weld. So keeping our travel speed up, but also maintain that balance between penetration and travel speed and heat. That's one thing we need to be aware of. This is all what's going to come in time as you develop your skills. So at the end of the weld, so we started the weld, we got the rod started, we're traveling along, we got the travel speed down, we get the end of the weld. What do we do here? Okay, well, this is where we have to terminate the weld. Terminate, just end the weld, right? So what normally people do is they will weld to the end of the joint, they'll get to the end of the joint, and they'll pause quarter second, half second, whatever you think is appropriate. Then they will remove the rod from the weld puddle, break the arc, and finish the weld. The reason we hang out at the end there is so we don't have a big hole in the end of our weld. Some of these rods dig holes. Some of these rods will basically dig a hole and fill it in with weld material. So pausing for that little quarter second at the end, half second, is going to backfill those craters for you. They're called craters. Craters are not a good thing. They can actually, large craters can cause weld cracking. It's called crater cracks. It starts at the crater and then it moves through the weld. So not a good thing. And it says backstepping is a short move in the opposite direction of weld travel. So you'll weld from here to here. We'll backstep just a little bit, pause for a quarter second, half second, fill that in, remove the rod, break the arc. That's how we get a good looking weld from end of plate to end of plate. So restarting a weld. This is what happens when you don't get all the way across a weld joint with one rod. Very common in industry, not so much in classroom, because we don't do welds that are a whole lot longer than 6 inches in here. But in industry, I've done welds that are 1.5 meters long, 8 foot, 10 feet long on plates. It's not a really big deal or anything too out of the ordinary in industry, depending on where you're working. So you got to know how to restart these rods, how to get them to blend together and look like you did that with one giant, amazingly long rod in one shot. And so the technique I use is very similar to this one here. So what we're going to do is we're going to strike the rod. We're going to start that arc. We're going to move that rod once the arc is established, back to the very back edge of the crater that you left with your last rod when you finished. You're going to let that start to fill in. You're going to start to move forward. Adjust your lead angle, backfill this crater from where you finished up, and continue rolling along that joint nice and easy. I'll show you that when you guys get into class. This diagram, it's hard to convey how it happens, how it works, but when we get in here, that's something I'll show you guys. All right, troubleshooting welds. So we got the basics. We got the starting of the rod, we got the travel speed, we got the termination of the weld. We have restarting of a welding rod. Now we're going to talk about what's good, what's not so good. We got a diagram here, a whole bunch of different weld beads, different sizes, different penetration levels. This is designed to show you what happens kind of on the inside underneath that weld, because you know we visually see the welds on the outside, but we don't really see what's on the inside. So here we have a plate, whole bunch of different beads and types of rods. Some small, fast travel. You can see kind of V shapes here. You see small penetrates just a little bit into the plate. Not appropriate if you're welding this size thickness of plate to another plate this size. You would have to use many, many, many rods to achieve a decent weld. Here with F, got a good looking weld for the most part. There are some inconsistencies in it I don't like. It might be, you know, operator error, whatever it is. I don't really, yeah. It's not as nice as I'd like, but whatever. It shows you the profile here. We got good penetration, decent bead profile. Here, we got a rod that's hitting quite shallow. We see it does not penetrate in the plate very much, but it's fairly wide. There's lots of spatter here too. So that's, you know, maybe not a desirable weld profile. I'd like you to produce some nicer stuff than that. Here, D, I think D is one of the nicer ones here. Got a good looking weld profile. It's kind of a combination of the C's and B's. Moved a little quick in some spots, but if we look at here, we got good penetration to the plate. Weld profile looks pretty good, fairly spatter free. This one here, C, looks like some 6010 style welding. Deep penetration, rough appearance, spatter everywhere, but they move too fast. You can see there's undercut here. It's just not a very visually appealing weld. I would not turn this in. I would not hand this over if I was a welder and I had a customer paying for a job. This is not something I would deliver to them. B here, we've got a fairly high profile. You can see the bead stacks up quite high, but doesn't penetrate that deep. So what this tells me is that this rod may have been run cold. Maybe they could turn the amperage off on that one, or maybe this is just a characteristic of the rod. And A, you know, decent width. I like the width of this one. The shape isn't the greatest. It's a little rough, but we got nice penetration here. No undercut, no spatter. Overall, decent. So advantages and limitations of shielded metal arc welding. Plenty of them. Plenty of advantages, plenty of disadvantages. With one, you always have the other, the yin and the yang. So we have low initial cost of this technology. It is not expensive in comparison to some of the other technologies out there. So there is that. It's nice and attractive. It can be affordable for a lot of people. Portable. In most cases, yes. If you're stuck to a big generator welder machine, then you got to become portable by using lots of cables. Cables are kind of expensive, and you do get some arc drop across longer distances. But we also have highly portable little welding machines nowadays. When I was in Fort McMurray, I was welding with a welder, stick welder, that weighed 8 pounds. It ran off of 110 volt electricity, used inverter technology to step up that electricity to something usable. And I had it on a shoulder strap. I literally threw that strap over my shoulder, carried this welder up and down ladders, and welded in all sorts of awkward to reach places. It was quite nice. So definitely portable. I was limited in the size of rod I could run. I could run 1/8 fairly well, but it generally worked best for 3/32 size rod. Ease of use outdoors. This is a big factor. Outdoors, we got wind, we got elements. Wind will take away shielding gas if you're using a gas metal arc welding system like we talked about in our last unit. It could cause a lot of issues. Plus, we got the gas bottle, the gas regulating equipment, the machine, the wire, whole kind of a lot of stuff going on there. Not that practical to take into awkward spaces. Yeah, so with shielded metal arc welding, we got all position capabilities. We can weld flat, horizontal, vertical, and overhead, no problem. As long as we got the right rods, we can do it. It's easy to change between many base materials also. So what you could do is you could weld something that is mild steel. You could adjust your amperage. You could grab an aluminum rod and weld aluminum. And you could grab a stainless steel rod, adjust your amperage again, and weld stainless steel. It's fairly easy to convert between different base metals. So some of the downsides, though, lower consumable efficiency. So we're talking welding rods here. That's a consumable in this whole kind of situation. Those rods, when we burn them up and say we got a big long weld joint, we can burn those rods up with probably 90% efficiency. We're only going to throw about 10% away. But sometimes rods get damaged. So then you lose some rods. If they're taking in moisture when they shouldn't be, that's not a good thing. You get a rod stuck, you break it off, you're kind of wasting a bit of rod there. Overall, generally, you get about 70% efficiency, 75% efficiency with shielded metal arc welding. Some people can run it more than that. Some people run it less than that. When I was downtown, I was running 1/8 7018 all day long on some big weld joints there. I used up as much of the rod as I could because we were going through lots of this rod. It would have been nicer to use a bigger rod, but the engineer's specifications said we had to use 1/8. Now, as a welder, we get to make some choices on things as to what's more efficient. But in this case, when you have an engineer saying, this is what you must do, you must follow that. So I used up as much as that rod as possible. We had to buy this rod by the pallet. We'd have the truck drive it to the bottom of the building, 45 floors down below. The crane would go down, pick up the entire pallet of rod. We're probably talking 1,000 pounds of rod here, fly it up to the top of the building, and that would last us a week. We would pour welding rod in and day out. I would go through a case of welding rod a day. So that's quite a bit of rod. But yeah, so it's, if it was wire, it wouldn't be so much, but that's the way it was on that job. It's hard to get wire up in those tight spaces top of the buildings. So you can see in this picture here, this guy's working in a shipyard. It's definitely not practical where he's working to try and fit a gas metal arc welding machine up in there. Another thing we see with shielded metal arc welding is it's hard to weld thin materials. Just the nature of the process doesn't really allow you to weld thin materials, whereas gas metal arc welding is much more suited to that, as well as things like TIG. TIG is well suited to it as well. Frequent restarts. Yes, you're going to go through that rod pretty quick. It might take you a minute to burn up that rod, then you're restarting another rod. You're also chipping off the slag at the end of that weld. You're brushing it to make sure you get a nice clean restart. So there is downtime between rods. So you got to think about that as well. What we have here is a higher operating skill, or a higher operator skill required for shielded metal arc welding than other processes. Some processes, when set correctly, almost seem to weld themselves. Flux core, dual shielded flux core, it's fantastic when it's set right. It welds itself pretty much. Very, very high quality welds with little chance of defects. Shielded metal arc welding is a different story. It requires the operator to have a high level of skill. You need to have a solid weld, solely steel, no inclusions of any slag or weld defects within the weld itself. When I was downtown, what we do is we would weld all week. We'd prep all of our welds. We'd have to stamp them with our initials, saying, hey, this is my weld. You would have to take full responsibility for that weld. On the weekends, testers would come in. They would do ultrasound testing on these welds. Now, ultrasound, the same thing that basically a pregnant woman gets on her belly. What they would do is they would apply the gel and they would take the scope and they would adjust the frequency and peer into these welds and have a look. And they didn't want to see any defects. They saw little dots in there, little reverbs coming off of the feedback of the ultrasound. Then that was a defect. That would get circled, highlighted, and then when you come in Monday morning, there'd be a big flag hanging off your weld, bunch of red paint on it saying, hey, this is where the defect is, it's got to get fixed. Fortunately for myself, I always took good care of my welds and I never came into a defect. In fact, I had to go fix a lot of other people's stuff, but different story for a different day. Got to be good with your hands with shielded metal arc welding, especially when it's becoming tested and they're asking for full penetration welds. So classification of electrodes is how we designate them and basically what the numbers mean on it. We'll get into this a little more as time goes on, but we're going to hit you with the basics for now. So when you look at a welding rod, you're going to see this on the end of it. You can see E70 and you won't see the XX. What you're going to see is something like an 18 or a 24. So the E just stands for electrode. That is the consumable part that creates a weld. The 70 is the tensile strength in KSI. That's thousands of pounds per square inch, not knowledge, strength, integrity. The YouTuber turned boxer. Yeah, so that is basically what that means is if you were to have a 1 inch square bar of this weld material welded perfectly, you should be able to hang 70,000 pounds off the end of that bar without deformation or stretching of that bar. This is a guaranteed minimum tensile strength when the operator does their part. The operator definitely has to do their part, create a solid weld for this to be as strong, but a properly welded weld can achieve much higher strengths than this one. We did a test at SATE where we did stuff like this, where we had to weld what was called dog bones. And then we would tear them apart using a giant machine. And we've had welds test at 125,000 KSI. So, or 125 KSI, basically 125,000 pounds per square inch of force is what it took to tear them apart. We'll see 60, we'll see 80, we'll see 100, 110, 90. That just basically means how strong the rod is. So the first X here, we're looking at this one. This is welding position. So if you see a 1, it's all position, can be used in all 4 positions. You can take it flat, horizontal, vertical, and overhead. It will perform well in all of those situations. But if you see it with a 2 on it, you got to use that in flat and horizontal only. Normally with the number 2, you're going to have a bunch of extra flux or steel powder, iron powder in the flux. That creates a bigger weld with using the same amount of core wire. The flux is just bigger. In turn, though, this is going to make it much more difficult to handle in out of position places. So you don't want to try and take a 70-24 into vertical or overhead positions because that's going to be no fun, not at all. It's basically going to be raining fire and steel on you, and that's not something we need to have. And the last X here is type of current and coding. So we'll see it 12, we'll see a 1 in 6011, we'll see a 0 for 6010, 6013, 7018, 7014, stuff like that. All of these charts or all of those numbers are going to correlate with ingredients that are in the flux. I've got some charts we'll kind of get into when we talk more about electrodes. It'll go over everything. It could be cellulose, could be rutile, could be lime, could be iron powder, could be a lot of different things in there. I don't have all of them memorized, so I'm not going to speak on that at the moment because I don't want to give you the wrong information. But when we go through the other slide, or the additional slideshows later on, we'll get all that information to you. So that is that for that, folks. We're going to end this here. We're going to stop sharing this. And yeah, that's what I wanted to go through with you guys today. Finish up the slideshow from yesterday. There is no homework today. No assignment to go along with this, but I will be building a test off of what we've done today. So this lesson is recorded. This is going to be available for you shortly for study purposes. So we'll have the slideshow by itself, no narration over top. Then we'll have the 2 back-to-back class lessons that I've narrated over, giving you guys additional information. This is all going to be study material for you. I encourage you to use it when taking these quizzes. That's why I provide it for you. So thank you very much for joining me today. I want you all to have a good day. It's looking decent out there. It's, hopefully the rain's going to stay away for a little bit. But yeah, just want to say thanks for tuning in. Hope you all stay healthy, and I will see you all tomorrow. Cool. Thanks, folks.